Hi there, Augie Kennedy here again with super awesome calculus. Well, we're still in chapter 2, and last time we covered limits at infinity and horizontal asymptotes. And today we're going to get into derivatives and something I've been talking about for a little while now. We're finishing up chapter 2, but first let's go ahead and look at the big problem from last time. Now you can see I have the equation written up here on the board because it didn't come out correctly on Microsoft Paint, because I messed up. But anyway, here's the question. When we study differential equations, we will be able to show under certain assumptions that the velocity v of t of a falling raindrop at time t is v of t equals v asterisk, v star, 1 minus e to the negative gt over v star, where g is the acceleration due to gravity and v prime is the terminal velocity of the raindrop. Find limit as t approaches infinity of v of t is the first thing I want you to do, and then I wanted you to graph the function if v prime or v star equals 1 meters per second and g equals 9.8 meters per second squared. And I asked, how long does it take for the velocity of the raindrop to reach 99% of its terminal velocity? Okay, so we're going to use this equation right up here, or this function right up here, and we're going to work with that. First thing is we need to find the limit as t approaches infinity of v of t. So let's look at that. The limit, remember the way we write this is the limit as t approaches infinity of v of t is going to be the same as the limit as t approaches infinity of v prime or v star times 1 minus e to the negative g times infinity, which are direct substitution, over v prime or v star. Okay, so what happens? Well, let's erase the top equation. We're going to work from bottom to top now. Let's look at this. What do we remember about limits? Well, the one thing that we should remember is the way the function e works. What we have here is the limit as t approaches infinity of v prime times 1 minus, and here's the key piece, e to the negative g times infinity over v star. Sorry I keep calling it prime. If we remember, e to a negative x value, to a negative x, looks like this. If we graph our function of e, if we remember that's the exponential function, we know that with a negative x value, it gets very, 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 very small. And if you remember, it's going towards 0. So basically, if you remember what we also talked about, which is the highest degree order thing, we realized that if t is infinity, then g and v don't really matter. So what we're looking at now is really the limit as t approaches infinity. Limit as t approaches infinity, v star times 1 minus e to the negative infinity, which is the same as 0. The limit of that is 0. And we get limit is v star times 1 minus 0, or v star times 1, which is just v star. So the answer is that the limit as t approaches infinity of v of t is v star. Okay. Now the second thing I asked you to do is to graph it. I can't blame you if you didn't graph it. This is a terrible function to graph. But if you did, maybe you used a graphing calculator, maybe you did it the old-fashioned way and plotted points. Regardless, you probably got something that looked like this. We have 1, we have 0, we have 1, there's somewhere around a half. We've got a horizontal asymptote up here, and we got, there we go. Okay? That's probably something along the lines of what you got. Now what I asked you to do is I asked, how long does it take for the velocity of the raindrop to reach 99% of its terminal velocity? Well, the way that we work this is like so. we know that Vt now is 0.99 V star. It's 99%. The way that you write 99% as a decimal, 99% of the terminal velocity is 0.99. So V of t equals 0.99 V star. That's something that we know. We also know that V star equals 1 meter per second, and g equals 9.8 meters per second squared. Okay? So the way that we write this now is we take the function and we replace Vt with 0.99 V star. So we have 0.99 V star equals V star 1 minus e to the 9.8 t, and we remember it's just 9 over V star, sure. And now we know that V star is 1, so we can just take out V star basically and just have 0.99 0.99, or let's write it as a fraction this time, 99 100ths equals 1 minus e to the negative 9.8 t. Because, yeah. Now, what we do is we're going to have to solve for t, because that's what we're looking for. We're looking for t. So let's go ahead and solve for it. So we have 1 minus 99 100ths equals, let's see, yeah, equals e to the negative 9.8 t. All right, just moving some things around, which is the same as 1 100ths equals 9, okay. We've got to get rid of the e. Now remember about remember about inverse functions. The thing that we need to do now is we need to calculate the inverse of the exponential function to work with that negative 9.8t. So what we need to do is we need to use the inverse of the exponential function, which, if you remember, is the natural logarithm. So the ln of e to the negative 9.8t, but we've got to do the same thing to both sides, so we take the ln of 1 100th, and what that gives us is the ln and the e cancel out, so we get negative 9.8t, and we get 9.8t, and then we get ln 100, or 1 100ths, and then we have t equals ln 1 100ths over 9.8t. And what's going to happen here is you're going to need a calculator if you want to solve an explicit 9.8, yeah. If you want to solve this function explicitly, what we're going to need to do is use a calculator and figure out that t is approximately equal to 0.47 seconds. What that means is that it's going to reach its terminal velocity, it's going to reach 99% of its terminal velocity after basically a half a second. So there you go. That's the big problem. It was a little harder than the last few, but we have a little bit shorter of a section today, hopefully. Okay. Now, today we're going to talk a lot more about derivatives. Wow. This is section 2.7 in the book, Derivatives and Rates of Change. If you remember, in section 2.1, right at the beginning of this chapter, I illustrated a parabola and the difficulty of finding the slope of the curve at a certain point that we called A. Or I don't know what we called it, but right now we're calling it A. So if x equals A, what is the point? What is the slope of this parabola at that point? In other words, and I said that the thing that we do is we'd find the slope of a tangent line. Remember, it touches the curve at one spot. Find the curve of the tangent line at that point. And the way that we do that, or the way that we did that, was we took 2 points. I'm going to call them P and Q, and we calculated the secant line. We calculated the slope of the secant line between P and Q, and we made P closer and closer to A and Q closer and closer to A. In other words, we made the secant line keep getting smaller and smaller and smaller in difference from the tangent line until there was no discernible difference. And that turned out to be, as we just discovered, the limit. And then we did something else regarding terminal velocity. We talked, I believe, about instantaneous velocity. I think we talked about dropping a ball off of the CN tower and the way that would work. And we learned that the way that you do that is we would figure out 2 points. If we were asked what the time if you drop a ball off the CN tower after 5 seconds, how fast is it going at exactly 5 seconds? Well, what you do is you figured out the average velocity between, we need to know 5 seconds. Okay, well we found out what it was between 4 seconds and 6 seconds. Then we found out what it was between 4.5 seconds and 5.5. Then 4.9 and 5.1. Then 4.99 and 5.01. And eventually, we saw that those numbers were getting close to something that we would later call L, the limit, which would be the answer to an approximate answer of what the instantaneous velocity after 5 seconds is. Now, what that is basically discussing or describing is one of the 2 fundamental branches of calculus that we're going to be talking about, and that is that of the derivative. And the derivative is exactly this. It is the slope of a tangent line to a curve at a certain point. And the way that we examine this is, we remember we have a curve. Here's the point. Here's the tangent line. We need to know the slope. Okay, we have 2 points. Secant line. 2 points closer to this point, A. Then we've got a secant line that's closer to the tangent, closer to the tangent. And the way that we write this, if this curve right here is f of x, okay, and this point is A, I'm going to make it a lowercase a, this point is A. The way that we write this, the tangent line, is the slope is m equals the limit as x approaches A of f of x minus f of A over x minus A. This is very obvious. This is the same, almost the same as a normal slope function. Remember, m equals rise over run, change and rise, change and run. That's what you're looking at here, except you're looking at it as it comes to a limit. That is the tangent line. Now with a velocity, dropping a ball off the CN tower and using different intervals of time, we come to something very similar. VA, if we want to find a velocity at a certain instant, it's the limit as h approaches 0, as those intervals go to 0, of f of a plus h minus f of a over h. And it turns out that these 2 things are basically describing the same thing, and that is the derivative. So here is what the derivative looks like in terms of a limit. If we have any function, the derivative, we have any function, f of x, and we want to find it at a number a, the way that we do that is we look at it like this. F prime, little apostrophe, a, equals the limit as h approaches 0, as points get closer and closer to a, of f of a plus h minus f of a over h. Okay? And in general, you can write it like this. F prime A is limit as x approaches A, f of x minus f of A over x minus A. That's what the derivative is. It looks like a slope, and that's what it is. So, what we're going to do is we're going to show that this definition of a derivative actually works. We're going to prove that it actually, or we're not going to prove it formally, but we're going to show an example of how it works. Let's take a slightly more complicated function than our usual x squared by adding some things to it. F of x equals x squared minus 8x plus 9. Now I know the derivative coming in, and you're going to learn it. It's going to be 2x minus 8. It's going to be 2x minus 8. So we want to find the derivative of this function at some number a. F prime at a. Well, the way we're going to do this is we're going to look at it like this. F prime a equals the limit as h approaches 0 of f of a plus h minus f of a over h. Okay? So let's go ahead. Let's move forward. That's the same as saying, I'm going to need plenty of space to write this, the limit as h approaches 0. Now we're going to plug in a plus h here. So where there's an x, we plug in a plus h. Limit as that approaches 0 of a plus h squared minus 8a plus h plus 9, okay, minus that quantity, minus a squared f of a minus 8a plus 9. Notice how we just replaced a and h with x over h. Now what happens is you've got to expand this, and you remember how to expand polynomials. It's not so rough. What you end up getting is the limit as h approaches 0 of a squared plus 2ah plus h squared minus 8a minus 8h plus 9 minus a squared plus 8a minus 9 over h. And then you're going to find out that a whole bunch of things drop out, and you're going to get 2ah plus h squared minus 8h over h. But remember here, we ask as the limit goes towards 0. So we're going to divide by h, and we're going to get limit as h approaches 0, because we can't use direct substitution here, or else we're going to get 0 over 0. So we divide by h, common factor there, and we get limit is 2a plus h minus 8. And if h goes to 0, we can do direct substitution. That limit is 2a minus 8, which is exactly right. So the derivative, what we would say then, is that the derivative of the function, if f of x equals x squared minus 8x plus 9, we would say that f prime x equals 2x minus 8, and at a certain point, if that point is a, f prime a is going to be 2a minus 8. Okay? Now this can work with any function. You can try it. You might want to try it with x. You might want to try it with x squared. Try it with x cubed. Try it with e to the x. Something interesting happens with e to the x, but we'll see if you can figure that out. So try that function and see what you get. All right. So I told you it was a pretty short lesson today. But what we're going to do now is we're going to use a very practical application. It's an economics application for the big problem. And here's the question. The cost in dollars of producing X units of a certain commodity is c of x equals 5,000 plus 10x plus 0.05 x squared. I want you to find the average rate of change of c with respect to x when the production level is changed from x equals 100 to x equals 105 and from x equals 100 to x equals 101. Then I want you to find the instantaneous rate of change of c with respect to x when x equals 100. And for you economists out there, this is called marginal cost. Now remember, what I'm asking here is for you to show me a rate of change. A derivative is all basically just a rate of change. So you can go ahead and you can plug in the values for 100 and 105 and show the average. But eventually you're going to need to use that formula that we just went over, the derivative formula, to figure out the instantaneous rate of change. If that formula seems a little cumbersome, it is. There are great shortcuts that'll make this a lot easier, and that comes in chapter 3. But next time we're going to close out the chapter by talking about the derivative as a function. Alright, till next time, take care.